Good afternoon, and welcome to a new food4Rhino webinar. Today, we are going to talk about the marine design plugin Orca3D. Thanks, Larry Leibman and Bruce Hayes, both Naval Architects and founding partners of Orca3D, and also Stéphane Dardel, Naval Architect at NDAR. This is the European distributor of Orca3D. And well, between the three speakers, they are going to show us what's new in version 3 of Orca3D, with a special focus on the new Advanced Hydrostatics and Stability module. Please feel free to use the chat. We are going to take care about it. We are going to collect your questions, and then at the end, during the last 10-15 minutes of the webinar, we will pass the questions to Larry, Bruce, and Stéphane. And we are also recording this webinar. This means that between when it finishes, or between today and tomorrow, it will be available on our food4Rhino playlist on YouTube. Just in case you miss a part of it, you will be able to watch it full. So, Bruce, Larry, Stéphane, many thanks for being here. Many thanks for organizing this webinar. And feel free to start with your presentation and live demo.
Okay. Can you hear me okay, Carlos?
Yes.
I see my screen. Okay, good.
Mm-hmm.
Thank you. Thank you for facilitating this, Carlos. We really appreciate that. So, and welcome everybody to this webinar where we're going to be talking about updates to Orca3D version 3 and also the new Advanced Hydrostatics and Stability module. I guess Carlos has already basically done this introduction, but quickly, I'm a Naval Architect and partner at Orca3D. Next, we'll hear from Larry Leibman, also a Naval Architect and partner, and Larry leads our development team at Orca. And then we'll hear from Stéphane Dardel, Naval Architect at NDAR. As Carlos mentioned, they are the Orca3D master reseller for the EMEA region. So a brief overview on Orca3D for those of you who aren't familiar with it. Obviously, it's a plugin to Rhino. It was first released in 2008, and we have currently something over 3,000 users worldwide in all facets of the marine industry, naval, commercial, recreational, educational. I probably should have mentioned offshore as well. So Orca3D has multiple modules and different feature areas, and we'll begin here with hull design and fairing. So here we have hull assistance for rapidly generating 3D surface models of various types of vessels, and then you can continue to edit those surfaces once you've created them with the hull assistance by moving control points. As you move the control points, you can also have real-time sections, that is stations, buttocks, and waterlines, update in real time as you move those control points. We can also do real-time hydrostatics. Again, as you're moving control points, you see the hydrostatics update, and lines, plans, and offset tables. And there are some other tools in this module as well, but those are the highlights. Next is basic hydrostatics and stability. So if you are an Orca3D user or have used it in the past, this is the legacy hydrostatics that you're used to seeing. So the hallmark of this is very forgiving model requirements. And by that, I mean, you don't need to have a closed surface or closed poly surface to compute the hydrostatics. You can have gaps, you can have small overlaps, you can even just have half of the hull. And it's very flexible in computing the hydrostatics that way. You can do any type of vessel. The example you see here on the screen is a platform for a wind generator. And I wanted to point that out because it makes a point that we don't do the hydrostatics based on stations. We use the surface mesh. So non-ship shapes like this are very easy. Multi-hulls are very easy. We do use stations for a few things like the sectional area curve and the prismatic coefficient, but the majority of the calculations are done on the surfaces. You can specify the condition that you want to analyze by one or more flotation planes. That could be a sinkage, trim, and heel combination. Could be draft forward and draft aft, or it can be by mass properties, a weight and a center of gravity. or you can even combine those two. So you might have a weight and a trim angle, for example, that you want to analyze. We do hydrostatics, stability, stability criteria evaluation, floatable lengths, and cross curves. But remember, in basic hydrostatics, there's no tanks or compartments, and so no free surface. That's handled in the advanced stability module that we're going to be seeing in a few minutes. So these two features make up what we call the design module. Next is speed and power prediction, and this is parametric resistance prediction methods, including the Savitsky method for planing hulls, the Hultrup method for displacement hulls, and new is the Van Ortmerson method for tugs and trawlers. Next is weight and cost tracking. So the concept here is that you build up your own library of materials, and these can be point, curve, surface, or solid materials. And for each of those materials, you specify a weight density and optionally a labor cost and material cost density. So by density, I mean, for example, for a surface material, you would give it a weight per unit area. Then you can assign these materials to objects in your model. And as your model is updated and modified, Orca computes the total weight and total CG, also the cost if you've entered that information. And you can then generate reports. You can export to Excel, and you can use the overall weight and CG as input to your hydrostatics calculations. So next is CFD pre and post processing. So this is not the actual CFD simulation, but this is where you create the input files for the CFD simulations. It's also where you create reports with the results from the CFD simulations. And it's also has the ability to create renderings with the free surface from CFD. So this free surface was computed in the CFD software and imported back into Rhino and Orca and used for rendering. So these three together make up what we call the analysis module. Next is advanced hydrostatics and stability. We're going to hear more about that in just a moment. And then the Orca3D Marine CFD module. So this is the actual CFD simulation software with our partner Cimerix, and it's an accurate, affordable, and easy to use CFD solution and runs on your desktop. So the idea is to bring advanced CFD capability to the Naval Architect's desktop. If you are an Orca3D user and you're upgrading from version 1 or 2, just so you understand these modules and how they map, what used to be called level 1 is equivalent to the design module, and what used to be called level 2 is the combination of the design and the analysis modules together. Okay, so let's look at some new features in particular. In the hull design feature, we now have something called multiple section lists. So in past versions of Orca, you could set up a table of stations and buttocks and waterlines, but it was just one table. Now you can set up multiple sets where you begin by naming the list. Then you select the uses, and the uses can be hull design and fairing, can be lines, drawings, and offsets, it could be hydrostatics or some combination of those. You also then select the objects that this list should be applied to. So different lists can apply to different parts of your model if you want to. And then the visibility is controlled by the layer. So we create a layer for each of these lists, and you can turn them on and off in the layer panel. In basic hydrostatics, we've added something new called fixed load cases. So in the past, we had something called the design condition. That's gone now. Now you can have as many of these conditions as you'd like to define, and we call them fixed load cases. So you begin by naming the case, then by defining the condition, which again can be a weight and a center of gravity, or a definition of the flotation plane, or a combination of those. Simply click the Save button. And then the list of saved load cases will show up in this panel. So there's a new Orca3D panel here, which you'll be seeing more of in a moment. But one of the tabs is fixed load cases. So you could select from your list of load cases here to rerun the hydrostatics, for example, if your model has changed, or to use it as the condition for real-time hydrostatics. They can also be used as input to other analyses like Savitsky analysis, for example. One important thing to remember about hydrostatics and the other routines like Savitsky and Holtrop and so forth is that the hull form does not need to have been created with Orca's hull design tools. It could have been created just with Rhino's native surfacing tools. It could even have been imported from another tool. We've also added floodable length analysis, so you can input the locations of the points you want to compute on the curve, the permeabilities, you can nominate bulkhead locations, say how many compartments you want to have flooded, and include a factor of subdivision. Here we see the floodable length and curves and the report. And you can see that the 2-compartment flooding did not pass in this example. In speed power prediction, in particular in the Savitsky analysis, we've made it easier to select the geometry. So now it's now a 2-step process. So the first step is to select the surface or surfaces to be used for hydrostatics. The next step is to compute the planing, to select the planing surfaces. So I don't need to split or explode or anything. I can just select these pieces of this surface to use those for the planing analysis. Then I can input the mass properties here, as always, but as I mentioned, you can now also select from one of your fixed load cases. And again, we've added a new method, the Van Ortmerson method, for tugs and trawlers. In the weight and cost tracking module, we've now given you the ability to specify the location of your stock material library. And this is useful if you're in an office environment where multiple people are using the weight and cost module, and you want to make sure that everybody's using the same library so that the models are consistent. So you could put the library on a server and have everybody point to that file on the server. Weight reports can now be grouped by Orca material in addition to being grouped by Rhino layer or Rhino group. In the CFD pre and post processing, there are a couple of new features actually. The first one here is resistance with propulsors. So what does that mean? It's essentially a self-propelled run, but it begins by towing the model to get it up to speed. So if you do a self-propelled run, usually the propeller is accelerating it, and that can take a long time. It's a realistic acceleration phase, but the simulation takes longer. In this method, you tow it up to speed, which gets it to speed very quickly, remove the towing force, and let it come to equilibrium with the propulsor. So that just saves a little bit of simulation time. The other new thing is the wake survey feature. So here you define the propeller disk. You can also copy it from a propeller if you've already set up a self-propelled run to get the same information here. And this is an example, typical example of a wake survey report showing you the nominal wake fraction here. So Orca version 2 is compatible with Rhino 6 and 7, but version 3 is compatible with 7 or 8. So if you're using Rhino 8, you need to be using Orca version 3. We've always in the past offered perpetual licenses, very similar to Rhinos. We now also offer the option of an annual license. So with a perpetual license, you receive any minor updates. So if we went from version 3.1 to 3.2, you would receive that. If we released version 4, it would be an upgrade, just as it's always been. With an annual license, you receive both minor and major updates. So 3.1 to 3.2, you get that update, as well as going from 3 to 4. And we've selected a new reporting tool, and so improve the reporting throughout the program. Reports are now saved with the model. So if you've got a Holtrop prediction or a stability run that you've run in the past, you don't need to rerun them if you want to look at the report. You can just open the report directly from the model. You can print or email directly from the report viewer. You can add watermarks. You can search within a report, and you can export to a number of different formats. Okay, with that, I'm going to turn things over to Larry and let him get started on the advanced stability demonstration.
Thank you, Bruce. Are you able to see my screen?
Yes.
Great. Okay. So as Bruce mentioned, my name is Larry Leibman, and I'm the lead developer at Orca3D and a partner. I'm going to walk through a demonstration of creating a model that's suitable for an advanced stability analysis, part of the major new functionality of Orca v3. Before I do that, I just had this one slide I wanted to present to you that shows what we call the Orca3D product model structure. As Bruce noted, with the basic hydrostatics, there wasn't a whole lot of additional information other than the geometry that we needed in order to perform the analysis. But with the introduction of advanced stability, we have a lot of additional information, things like what compartments are tanks and what fluids they contain, what their permeability is, where bulkheads and decks are located. So this required a little bit more organization of the attribution in the model, and we use this Orca3D product model to represent that. At the highest level of the model is your Orca3D design, shown here in yellow. That's your full model that you're going to analyze with the advanced stability capabilities. And you can have multiple designs in your model. Typically, you'll have one, but if you want to have different designs that you're comparing different subdivision with or different size hulls with, you can have multiple designs. Within a design are the geometry components. We call these displacer components, but these are really the geometry that makes up the design. These components all consist of solid polysurfaces or volumes. So you can see here, I have in red the hull component, but in addition to that, you see in the list are skeg, bridge, and accommodations components. So it's up to you how you want to break up your model into components. Within a component, we need to subdivide it into individual closed volumes, which we call spaces, but we also use the term compartments. Typically, the difference is a compartment can have one space or more than one space. So spaces is the most granular level of subdivision, and usually it's a one-to-one relationship between a compartment and a space, but as I mentioned, you can have multiple spaces within a compartment. And if a compartment has fluid in it, we call it a tank. So this is sort of how we break up the model for advanced stability. The nice thing is all of this creation of this, which I'll show in a moment, is largely automated. But this panel showing the product model structure gives you the ability to interact with your model and select compartments, for example, in order to set their attribution. So I'm going to go through the process now of creating a simple subdivision model. And as Bruce noted, the geometry can come from anywhere. For this example, I'm going to start using the Orca3D Hull Assistant. And as you can see here in the Hull Assistant, we have assistance for different types of vessels. And in the Ship Assistant, I've saved a model, which I'm calling the Webinar Ship with No Bulb. And if I open that and preview it with sections, you can see what the shape of the model is. So of course, you can adjust all these parameters and change the shape. And once you do that, save the settings in your library, which I've done to pre-save this model. So I have this model pre-saved. I'm going to go ahead and create the full model, which now adds it into the Rhino document. The next thing I'm going to do in order to start building my design is I'm going to join these surfaces into a single closed volume. So this is going to be my hull component. To make it a little bit more interesting, I've created a box, which I'm going to use as a cutter with the Boolean difference command. I'm going to subtract out this volume to make it a little bit more interesting of a hull with a step in the deck. So this is a very simple way to create my hull component. I've also have some other geometry that was created a priori. I have deck house components, and you'll see here I have a skeg component. These are all solid geometry and will be added to my Orca subdivision model. So the way to do that is create a design. So I'm going to create a new design by clicking the toolbar button to run that command, and you can name your design. And part of creating the design is adding your components. So my first component's named hull, which I'm just going to select my hull component and accept that. Now I'm going to go ahead and create my other components, the skeg. So I gave it a name, selected it, accept that. I'll create an accommodations component, which is the first level in here. And then the second level I'm going to call the bridge component, accept that. And when I'm done, I get a warning that some of these components may overlap a little bit, and we want you to be aware of that in case there's any significant volume overlap. There's not in this case, but you don't want components to have major overlap, especially if they're displacer components, because the displacement can then be double counted, which in general you don't want to have. So what you can see here, there's the Orca panel, and the first tab is my product model, which I was showing in the slide earlier. You can see I have one design that I created with 4 components. And each of those components, I'll look at the hull, for example. There's the hull component, has one compartment in it. So the model, a component starts out by default, generally speaking, with a compartment in it. And our task now is to start subdividing these components as needed in order to develop our compartmentation model for the advanced stability analyses. Now, I'm going to go ahead through the process of subdividing the model. Before I do that, though, I'm going to take advantage of a tool we call frame systems in Orca. Frame systems are very useful for defining locations of bulkheads and decks and things like that. So this is our form for creating frame systems. You can see one thing it has in here is the ability to define your aft perpendicular and forward perpendicular. This is useful not only for output from hydrostatics. We now can show you, for example, the draft at the AP, draft at the FP, but it's also used for input. But you have to define where the AP, FP, and baseline of your model are in order to take advantage of this. You also see here we can place the origin of the frame system. So if you want the origin at the AP or the FP or somewhere in between, you can place it there and you can orient it however you want. I'm just going to quickly go through here and add some longitudinal frames. These are frames spaced along the longitudinal direction or longitudinal axis. So I'm going to add 1 meter spaced frame from 0 to 10 meters, 2 meter spaced frames from 10 to 40 meters, and then go back to 1 meter spacing from 40 to 50. And what you see here is that you can have a non-uniform spacing. I'll show the frames, and they show up here in your list. So you can use these frames for snapping, for inserting bulkheads, things like that. You can also define frames in the vertical direction at deck locations or in the transverse direction. So what I'm going to do here is run a script that I've preset to create my frame system. All of the commands that you're seeing here for subdivision are scriptable. So this script just created its own frame system with both not only longitudinal frames, but also vertical and transversely oriented frames at key locations. So that's the idea of creating the frame system. So now I want to actually start the subdivision process. And there's several different ways and tools available in order to subdivide your model in Orca3D. The first one I want to show, which is probably one of the simplest but most commonly used, is transverse decks, bulkheads, and horizontal decks, transverse bulkheads, and longitudinal bulkheads. So when you run the subdivide command, you have to first denote which component you're going to subdivide. You can see I've got my 4 components, and I'm going to click the hull. You can notice immediately that as soon as I move my mouse, you're seeing it snapping to these various frame locations that I predefined. So this is one of the real advantages of having a frame system defined. It's not required, but it does make things a lot easier in terms of insertion of decks and transverse bulkheads. So I'm going to place several transverse bulkheads in my model here. And now I'm going to change the type from transverse bulkhead to horizontal deck. So while you're adding these planar subdivisions to your model, you can change the orientation. And I'm going to add a deck here at my main deck height, so you can see it snapping there. And when I accept this, you can see my model now has multiple compartments. They're not all just one compartment components. In fact, if I look at my tree, you can see now I have individual compartments which have all come about as a result of adding these planar subdivision. As part of this model building capability, we've added some visualization capabilities to make it easier to work with these subdivided models. And probably the most significant one is the clipping box. So I can define a clipping box and now show the internal subdivision in my model and the various compartments, okay? One of the other ways or pieces of functionality for subdivision is deleting faces. So let's say on this compartment 0, 5, and 6 that I have here, I really don't want these bulkheads to go all the way up through the deck. I just want that to be one open deck. There's a command in here to delete faces or remove faces. So I'm going to select these two faces. It's going to let me know that it's going to affect these compartments. And you can see now I have one compartment. It's called compartment 0, located right there in above the deck. So that's another feature, is the ability to delete faces. Okay. The next feature I want to talk about is still related to adding planar, in this case, a horizontal deck, but it's using this option specify compartment. So that lets me say, I don't want to put a deck through the entire model. I only wanted to put it in certain compartments that I select. So I click specify compartment, and I'm going to place this deck in just compartments 4, 8, and 9. Okay, and I'm going to say I want to put a tank top in. And you'll see when I do that, it's only inserted that deck in those compartments that I've selected and not in other compartments. Okay, so so that's another useful feature, and probably the most used or flexible, I should say, subdivision technique is the ability to use custom Rhino geometry in my model. So I have a layer here where we've predefined some custom geometry, and it has a lot of different geometry, and it's very useful for inserting things like small rectangular tanks or tanks that intersect with your hull. So I've got these two tanks here right now, and if I want to add those to my model, I click on Subdivide Model, select my hull, and I use the type of custom geometry. And with that, I'm going to select these two boxes that are just regular boxes in my Rhino model and accept those. And I'm going to turn that off. And you can see it's created, it's a little hidden now because I've got the cutting plane on, but you can see that it's added those two tanks to my model. So taking that a little bit further, I'm going to go ahead and turn on all of these additional pieces of geometry, which are unusually shaped geometry that intersect with my model. And I'm going to go ahead and use that subdivide option to subdivide my hull. I'm going to select the type of custom geometry. I'm going to temporarily turn off my hull and select all the geometry, accept that, turn off those layers, and turn back on my Orca hull. And you can see it's added that all as individual compartments with individual names to my model. So custom geometry allows you to take just about any piece of geometry in your model that you can create in Rhino and incorporate it into your subdivision model. So this process you can carry on. There's some additional longitudinal bulkheads, things like that we want to insert in our model. So I'm just going to open another file here where I have made all those additional changes, and you'll see it's got some more subdivision in here. And if I turn on the cutting planes, the clipping planes again, or clipping box, you can see what the internal subdivision looks like for this model. Okay, so that's the basic process of creating your subdivision model. Now, but in order to make use of this model in the advanced stability analyses, we have to be able to assign attribution to these various compartments. Some are tanks, some are not, some are displacement components, some are non-watertight. So we have to be able to assign this attribution. In order to do that, to be able to assign fluids to tanks, we need to use fluids that are defined in what we call the Orca fluid library. So this is a predefined set of fluids that we make available automatically. All the gray items in this list were predefined, and you can see they have a name, a density, and a color. The white ones are ones that I've added. They're custom fluids. So you can add your own fluids with their own density to this list as well. And these are what are used in order to populate tanks with fluids. So that fluid library can be passed between users in an organization, and so that you're all using a consistent fluid library. So the process of assigning properties or attribution to a compartment or space in this case is very simple. There's a compartment properties command. When you select one or more compartments that you want to set the properties of, you select it, accept it, and you can give it a name. Maybe this is a forward ballast tank, and it has a permeability of 0.98, and I say it's a tank. By default, it is not a tank. It is just a compartment. That's all, an empty compartment. But when you make it a tank, you have the option to assign a fluid to it. For example, seawater. You can define a sounding tube. We have options to define different impact and damage permeabilities. But when I say OK, it now is renamed that. And there's an option in the View tab to show the color tanks, or rather compartments, by their contents. So that tank is now showing the color of that fluid. And you can easily adjust that as needed on a case-by-case basis. Another example, I'm going to select this time 2 compartments, these accommodations and bridge compartments. And you'll notice I can't set the name because I've selected multiple compartments and they have to have different names. But I can set their permeability together, and I can make them non-watertight. So in this case, I want to say the accommodations and bridge levels are not displacing volume, but they are used for things like computing the sail area when using a healing moment. So this is an easy way to set them to be non-buoyant or not watertight. There is an option to display down here in the View tab compartments by their type. So we show non-watertight compartments in the cyan color, and tanks in green, and so forth. Okay, so you can go through that process of naming and assigning properties. And again, I have a script here that I'm going to run real quick that does all of this, so we don't have to sit here and wait for me to do it. And basically, again, showing the scriptable capability of these commands. And you can see how it's gone and set different tanks with different contents and different compartments with different names. Okay, so so that really is the whole process of building a subdivision model and attributing the default fluids and characteristics of the various compartments and tanks in the model. Now, once you've done that, right away, you get some added capability. For example, I can come in here and run a tank tables. So if I say create tank tables for this model, you can choose your trim angles, your heel angles, and the quantities that you want to vary in your tank table. In this case, it's a load fraction or percentage full going from 0 to 100. So when I run that on this particular model, it goes ahead and uses Excel for that calculation and populates the tank tables. So for each tank, it shows you its contents, the density of the fluid, the permeability, and it gives you this table. You can see how my percentage fulls are varying in 10% increments, and it gives you the volume, the center of gravity, free surface area, and free surface moments, and it does that for each tank, and they're color-coded according to the tank contents. So very simple to create tank tables. Let me close this. Another useful analysis you can do is reporting area and volume for this design. So what that does is it goes ahead and extracts all of the volume information for each component, the total volume, the deck locations, and transverse bulkhead locations, as well as for each compartment, you get the area and volume and centroid, and how much of that is deck area and so forth. So this can be very useful design information, particularly in early stage design when you're trying to figure out weights and so forth. Okay, the last two things I want to do here is first I want to show you, we get the question a lot is what happens if your geometry of your hull changes now, right? You've gone ahead and created a model, but there's a change to the geometry of the hull, for example, the hull component. How do I handle that? Well, over here in my Rhino layers tree, I have a layer here showing the what I call a modified hull. So in this example, the modified hull has a bulb added, and it's also got wider in this case. So you can see that the hull's gotten a little wider, and it's also got a bulb on it. So there is a mechanism here for us to swap the hull geometry. It's called Orca replace component geometry. And the way that works is you select the component whose geometry you want to replace, in this case, the hull, and then you select the replacement geometry for that component. So I've gone ahead and run that, and it's given me a warning that I want to check some things afterwards. You always want to go back and check your model, but you can see the new design now has the 4-peak ballast tank, including the bulb, and the wider hull, but otherwise it's kept the same subdivision model. So that's a powerful tool for replacing or making changes to your geometry and still maintaining the subdivision model that you used. The last thing I want to talk about goes back to PowerPoint for a second. I just want to show you one different slide. Everything that I've been talking about today so far uses what I sometimes, or I've heard called a ship-centric or outside-in modeling process. You take a component, in this case the hull component, and you start adding bulkheads and decks and other custom geometry to subdivide the model into components. And that's the default behavior that I just showed you as an example. But we have other times where people take a more what I call platform-centric approach, or inside out. In other words, they view the hull design as just something that has to be wrapped around a platform that is serving a particular purpose. So they design all the innards, the inside portions of the model, what it is in terms of area and volume they need, and then they wrap a hull around it. And the idea here is to show you that this mechanism is supported with the advanced stability model in Orca3D as well. I'm going to open up another model where in this model, you'll see that we have, let me turn off the hull for a second. We have a whole bunch of internal geometry that was defined before the hull was, and then we want to use that and wrap the hull around it. So I've already pre-created a design here which just has a single hull in it. It's the hull that you see here, and I'm going to come over here and I'm going to temporarily turn off some of this geometry. And what I'm going to show you is that the ability to subdivide with custom geometry, changing the type to custom geometry, allows you to use this approach where you predefine all of your internal geometry, and then you can see now as I turn on the hull, it's added that. So effectively, I've added these internal compartments just by using custom geometry for all of the internal pieces of the model. And if I wanted to change that, I could change those internal pieces and reuse that custom geometry to update my topology. So I'll do another one as an example. I'll turn on the water ballast tanks. I'll go ahead and subdivide this model with custom geometry and temporarily turn off this so I can select everything. Okay, it should be done here. And you can see how it's broken up these individual pieces of the model. So this is another powerful modeling approach that I wanted to show you, where you can use a sort of inside-out approach to building your model. So with that introduction to building the subdivision model, how do you go ahead and do the analyses that we are available in the advanced stability module? I'm going to pass it over to Stéphane in order to allow him to continue showing the process of performing the analysis. Stéphane?
Sure. Yeah, let me share my screen.
Wow, amazing. Just while Stéphane shares his screen. Maybe one question you could answer now, Larry, from Paris Sagand. How is the shell thickness incorporated into the model?
Good question. Currently, we don't. You would have to, and we've had people do this, actually model it. We've had people do an offset, a small offset to account for shell thickness, and have it be its own component. But what we're planning on doing, what we have in our development, is the ability to allow the user to specify a shell thickness directly. So that's on our development list to add. But right now, you would either have to model to the outside or inside of the geometry, depending on what information is available. Bruce, I didn't know if you had any additional thoughts.
Yeah, I just to add to that, we had one user that wasn't doing shell thickness, but a similar concept, and this was insulation around a hold in a fishing vessel. So they began by creating the outer portion of the compartment, just like you've seen Larry do. They then used that in Rhino and offset it inward by the thickness of the insulation. And they could join those and essentially create a compartment that is the insulation that has a permeability of 0. So in that case, unlike shell thickness, it's actually a pretty significant amount of volume that you need to account for. And it shows that when you're doing the calculations on surfaces rather than sections, it's easier to handle cases like that.
Okay, so many thanks for the answer. Maybe you can add this to the FAQ section on your website. And yeah, please, Stéphane.
Sure, thanks. So thank you. My turn to thank everybody for being present. So I'm Stéphane Dardel, Naval Architect at NDAR. I was introduced a bit earlier, so I will make it short. NDAR, we provide software solutions to the marine industry in Europe. Okay, so and Orca3D and Rhino are very central in our solution. So and I had the chance to accompany Bruce and Larry into this development of the advanced stability. I'm certainly not a developer here, but I had the chance to be involved into how the tool would be implemented and developed, and sharing ideas and a bit of brainstorming here and there. Okay, so I would like to I would start with from my own model, but it's what you see on my screen. It's meant to be a motor yacht, 50-meter motor yacht. It's pretty much in the same state of maturity as what you've seen on Larry's screen. Okay, so we can tell the model is subdivided into compartments and tanks. You see the tanks are present here. They have been named. They have properties. So, for example, this one tank is called F403. Okay, and it's filled up with diesel oil. So at this point, I would like to show you how we make this model, this geometrical model, into an analysis. So I want basically to perform a stability analysis. So I want to load my model. I want to assign some to select some stability criteria, and then perform a rollover calculation checking those criteria. Okay, so just pretty much what you've seen so far. I would use this side panel, okay, just like you've seen earlier with Larry, to control, to basically manage my my Orca3D study. Okay, for information, Orca3D is fully integrated in Rhino. You access it via pull-down menus here at the top. You access it via toolbars, okay, here, and also this side panel, which basically pretty much has everything in it. So it makes it very relatively easy and intuitive to navigate across the study. Okay, so here we speak about loading the model now, and we have the notion of creating load cases. So that would be in that branch of my Orca3D design. Okay, before I go into the details of the load case and load cases, okay, I will just introduce the notion of fixed load groups. And here's the intention. And I've created a few load groups that are probably typical of a motor yacht. The intention of load groups is that typically some fixed weight items that I will retrieve in all my load cases, or at least some of them. Okay, so it can be one single point. Okay, like for example, crew passengers effect keeps opening on the screen. Right. Of course, it has a weight. It has a center of gravity in LCG, TCG, VCG. But it can also be a more detailed. Like I played this for the light ship to basically be more detailed into how the different weight items are represented. Okay, but overall, all those weight items are now made available. So as soon as I create a new load case, I will be able to pick them up. And I will first start by looking at an existing load case, which is my full load. Now, if you allow me, let me create one from scratch here. So I'm going to close this one. I'm going to I want to create a new load case. So right click here and say create new fluid load case. Okay, top part is to give it a title, to provide some optional notes, and then this is where you control your tank fillings, and this is the list of your fixed weights. Okay, so I'm going to call this one LC02. This is obviously my own nomenclature, voyage. Right, and if you allow, I will start working with the fixed weights. Okay, I will just simply check the one that should be part of my load case. Effectively, the light ship, probably the tenders and toys. Provisions, I would pick the provisions 50% in that case, and then crew and passenger. And here I have already my overall fixed weight summation. And now let us focus on the tanks. Tanks can be filled up as a percentage, can be filled up as a sounding or an ullage, or as a volume in meter cubed. Right? I will just play the game of making it to this is a fuel oil day tank. I'm going to make it 90% and 90% this one. Right? And of course, as soon as you do that, it populates the weight and the center of gravity. You can, on a load case per load case basis, you can update the fluid. Okay, you can also update the permeability. Those are coming from the default settings in my geometrical model. Right. Well, I guess I can just put 50% in pretty much all my fuel tanks. It's meant to be a mid-voyage condition, including the freshwater tanks. I'll speak a bit later about the damage stability, but I can see here I'm only listing the tanks. I'm not listing the compartments. More about that a bit later. And the last one thing that you want to address here in the load case definition is the free surface model, the free surface types that you want to employ for that load case. And basically, we have two methods. Okay, that's bear with me. It's we have two methods available. One is the CG shift, and one is the free surface correction. I don't think I want to go too much into that detail, but effectively CG shift means that the software will keep recalculating the condition inside each tank, hence the center of gravity inside each tank. Whereas when you use a formal free surface correction, it's basically applying a constant throughout the rollover calculation. Somehow it does a VCG rise. Right, I will just leave it there. And when you pick up that artificial free surface, it is either the true, which is basically the current free surface moment. It can be the max free surface moment, or it can be a custom. Custom means that it's your own user input. I'm going to stick to CG shift. And at this point, I've made up a load case, and I will want to check if it's somehow complying with my trim. So I'm going to ask the solver, the software, to tell me what, in my case, what is the trim at forward perpendicular and what is my trim at the aft perpendicular, and eventually the residuary heel. Am I happy with that? Yes, no. I think I'm good. I'm just going to save that load case. Okay. By the way, you can also, in your graphical screen, you can insert the flotation plane. This is now actually effectively in the Rhino screen. So should you want to measure some dimensions, this is effectively a Rhino entity now. And you can also produce a hydrostatic report at that point. Let me just do that. We will look a bit further at reports a bit later, but that's my report for that load case. Okay. Again, I wish to come back to that a bit in a minute or two. Okay, I'm going to stop there. So now I have in my list 2 load cases, and I can have as many as I want. All right. We have a way, for example, to organize our sets of load cases. It can come to a point where you have a lot of load cases to handle. So we have this manager that will allow you to organize that into folders and subfolders. And here, for example, I'm going to create one folder that I'm going to call intact, because I want to distinguish what are intact load cases from damaged load cases. And this one I would call it damaged. Okay, and then I can simply drag and drop. So those 2 are meant to be intact load cases. So I do that. But hey, this one, perhaps full load, I will want to make it also, as a child, I want to make it a damage case. So I'm going to make a copy. And that copy, I'm going to drag it into the damage branch of my tree. I'm going to close that. And yeah, perhaps I could rename it at this point. I'm going to say LC01. So let me please invent a nomenclature that could be damage 1. Okay, I'm going to say close. And here I can now retrieve the same in my Orca side panel. I can retrieve my same hierarchical tree. All right. And for example, to create that damage case, I would just simply edit that fluid load case. And the only thing that I want to do really here is to set any one of my tank or the compartments to being damaged. Okay, I want, for example, starting from the back of my vessel, I'm going to start with the lazarette compartment. So it's not listed because it's not a tank. So I'm going to uncheck that button, and then I can now see the list of all volume, all internal spaces that includes watertight compartments. That's my lazarette. And I'm just going to set its type, its mode to being damaged. We support with Orca intact, damaged, and frozen. Frozen essentially means that we are neutralizing the free surface. That means that the this weight, this fluid load acts like a fixed load. Okay, and I will just simply save it. Okay, and that's how I can create as many load cases. I can copy one, I can duplicate at will, etc. And one last thing I wanted to mention, we've mentioned that before, but Orca3D is scriptable, and we've seen that with Larry a bit earlier, but it's also true with load cases. And I will just pick a simple script that allows me here, I'm just gonna bring it into my screen, that allows me to create another load case, which eventually I call LC03, arrival. And basically I'm setting the condition of my tanks, fuel oil tanks, fuel oil day tanks, and they are filled up with a percentage. Different ways to run a script in Rhino, but I will just simply at this point, Control C and Control V into the screen, into the Rhino program, the command line. Okay, and this new load case has been created here, and I only need to go and perhaps modify it. And essentially what I need to modify, assuming that my tank loads are right, okay, I probably want to update my fixed weights. So perhaps I will just switch off provisions and the rest can stay. Okay, so I've created that other load case. Right, I see that the time is flying, so I'll try to be concise. Before we do stability calculation, we want to possibly have some downflowing points. We call those points of interest. I'm going to manage that. Okay, and I can basically create points of interest by snapping to eventually to the Rhino geometry. Let's assume that I want to place ventilation right at the top here. Okay, I can snap directly into my Rhino geometry. I'm going to call that ventilation. Right? Is it a downflowing? Is it active? Yes, no. Is it a downflowing point? Yes, no. It can be a point of interest that is not active for downflooding purpose. Okay, and same like I did with the load cases. Probably I have a long list of points of interest rather than doing this manual input. I can certainly live with the script here. So I'm going to do the same with the script for inserting those 4 points of interest. Okay, the command that is used is Orca point of interest. I'm just going to copy paste that, and it's a very simple script. If you look at it, it's basically providing a description and a location along the X, Y, and Z coordinates. See, and I need to stop that, and then I'm going to paste that script here. Okay, and those points have been added to my list of critical points. Okay. We have the notion of curves of interest. So it's probably here the idea to monitor the freeboard or the margin line. I'm going to go back here and then curve of interest, manage curves of interest. Okay, and here again, I can leverage the existing Rhino geometry. Add, I'm going to select curves, and I will, in that case, select the actual deck edge along the full length of the ship. Okay, I'm gonna call it freeboard SB for starboard. Okay, and I'm gonna make it active for being a deck edge, and then I'm gonna make it mirror image. Just this mirror image, I will just rename it into PS for port side. Okay. I'm just going to delete that now. We are getting pretty much ready to perform our stability calculation. I would just like to mention that we also support healing moments. Let me show that to you. I will define a healing moment in the different models available. Okay, so healing moments, that would be that button in the current design. And we support all those different models, wind edge from the beam winds, okay, towing and tow line pulling, lifting weights from a crane, passenger crowding, etc., etc. I'm going to focus on this one, beam winds, okay, and I'm going to edit it just to show that we are able to leverage either the Rhino geometry. If I select this button Rhino geometry, I can then select effectively some Rhino polyline that would represent the outboard profile of my ship, but I can also leverage directly the Orca geometry. So here it's able to compute an overall area of 400 meters squared. Okay, so that's for the wind healing moment. I think I need to say yes, acknowledge. I skip all the other, let's say, settings that are not relevant at this time for the presentation. Next one is about stability criteria. So it would be this next button here at the top. I want to define stability criteria. And the philosophy with Orca3D is that the user is in control. Orca3D provides this interface that allows the user to compose his own stability criteria, with a strong notion as well to be able to import and export. So either you export just one set of stability criteria, or you can export your complete stability library, the stability criteria library. All right. I'm going to look, for example, at this Maritime Coast Guard, the UK agency, okay, that does that for this motor yacht, and I'm going to look at how those were composed. I'm going to edit that, and how it goes. It works with keywords, all right? So you can select, for example, typically the stability limit would be based on an angle, on an area under the GZ curve, a freeboard, area ratio, etc., etc. So if I will look in detail at this one, for example, edit limit, this one is defining an area between free equilibrium and the minimum angle between 40 degrees and flood. It's expressed in degrees, it's bigger, smaller, etc. Okay, so that's how you do composite. And just for the sake of doing something further here, it's already preset. I'm just going to add another one. I'm going to set a new one that I call, for example, it's going to be a check of the angle at, and I'm going to pick here the notable point of my GZ curve, which is the steady equilibrium. The difference between free equilibrium and steady equilibrium is that this free equilibrium, it's ignoring any heating moment contribution, whereas the steady equilibrium, it's basically the first intercept between your heating moment curve and your righting moment curve. So here I'm interested in checking the steady equilibrium. I'm going to invent something. I'm going to make it, I want to make sure that this angle is smaller than 7 degrees. Okay. And I'm going to add that to my set of stability criteria. Okay. Perhaps I'm going to do, because I set a curve of interest for the freeboard, I can also do the same with the freeboard at steady equilibrium. And I want this freeboard to be greater or equal to 1 meter. All right. If I try to say, okay, here, I'm going to say that this limit criterion is associated to heating moment. So I need to hook the heating moment type to that stability criteria set. Okay, so I'm going to select beam winds. Okay, hold on. So that's how we handle stability criteria. Now I'm going to go to checking that stability criteria. So I check one or several of my limits, sorry, of my load cases, and I'm going to run a stability criteria evaluation. Right, so you see that I can pick one or more, focus on the full load, and I'm going to pick the intact with that heating moment. Plenty of report options. This is also new with Orca v3. Okay, you can now select pretty much what you want to show into your report. So whether you want to make a very slightly somehow concise report or very complete report, you can do that. All right, so I will just basically leave those options as they are and press OK. And we now have this screen that shows you the progress of the righting arm computation. I can show the tanks. I can show the label of the tanks. All right, and I can orient my my point of view here. Okay, report is ready. Before we look at it, I would just like to say that we can always come back to any one point of that rollover calculation. For example, I want to focus on the heel 20 degrees. I can retrieve it. And should I want to output that as an image, so it goes to a JPEG image, I can also insert this flotation plane in my Rhino graphical screen. Here we go. This is my heel 20 degrees. Right? And that one is my report. A report would look like that. So again, I've pretty much checked all options, so it's a relatively complete report. This report can be exported to pretty much all formats: PDF, HTML, docx, XLS, CSV. So in case you wanted to do some post-processing to make this piece of work part of a bigger document, you can always do so, right? Let me scroll through the report. We have a graphical screen of representing the ship, the status of my different tanks. I'm just scrolling through a bit quick here, sorry. Okay. This is a view of my tanks. Would be if I check the damaged condition. So of course there is no damage here, but it would show the damaged ones here. I'm going to try to do that anyway, a bit of lack of time, but anyway. And check of my stability criteria. Here you go. It looks like I'm failing at least one criterion, right? So when it's green, it's passing the criteria. When it's red, it doesn't pass. And what's happening here, it's red because my criterion was 7 degrees of heel, and I achieve almost 8 degrees, so I'm failing my criterion. This is the status of my points of interest. Okay. Should it be damaged? Let me just take a look at what the damaged load cases look like. I'm going to use this view again, like we saw earlier, to see through the model. Different ways to view the model by content. So it's only showing tanks. By type, will eventually show what is watertight, what is a tank, different color codes, and what is non-watertight. So here I took the decision that the superstructure was non-watertight. And then the status would eventually show. It will be based on one or the other load case. For example, if I select this damaged load case, it highlights which volume or volumes are actually damaged or frozen or intact. Okay, I think I'm good because I'm also trying to be attentive to the timing. Just one comment is that all the stability report that I'm creating are actually stored within the 3DM. And more generally, all the work that we do with Orca3D is stored in the 3DM. There's no need or no notion of having to save the data in an external file that you would need to load into Rhino and everything. Everything is contained inside the 3DM file. So this is a history of the different report that I did on that model. So perhaps I can come back to this one done yesterday night. Okay, it's here. I can always come back to it. They are time stamped, so I can always come back to them. And of course, when I want to get rid of it, I can just delete it. Okay, and I can of course also rename it to something more explicit, more in line with my nomenclature. I think I'm good in terms of what I wanted to show. Bruce and Larry, do you think of something else that I should put forward here?
There was a question about customizing the reports. I don't know if you could show some of the report options.
Yes, sure. Yeah, let me go back here. Run stability criteria relation. So a button report options here. Okay, and those are the different report options. Okay, whether I want to show the graphical view of my ship, whether I want to show a report of my points of interest, I can check and uncheck, or the rating arm, the actual GZ curve. Do I want to show only the curve or only the table or both? And when it comes to the hydrostatic output itself, okay, you can really be very selective in what you want to show. Right? So some people may not interested in let's say documenting the surface meshing parameters and stuff like that. Okay, so yeah, I don't mean to show too much of it now because there are so many options, of course, that I would let you try, but that's what is made available.
Great, thank you.
Wonderful, Stéphane, and thanks also to Larry and Bruce that have been answering all the questions on the chat. There were many.
Yeah, I see. Thanks.
Yeah, I mean, I lost track of them, to be honest, because there were so many, but Larry and Bruce were really fast and
there are a few more that we still have to get to, but we can get to those offline.
Yeah.
As you want. If you want to answer this now, I mean, read the question and answer this so that all the people know about, feel free. We can extend a few minutes.
I'm catching up with questions here, so go ahead if you want.
So there was a question about a way to add a correction for a sine or cosine shift to the writing arm curves. We don't currently have that capability. And also, do we have options for the runoff of liquid moment shifts for damage stability analysis involving tanks? And again, no, we don't. We're doing loss buoyancy. So that's not a capability that we have. There was a question about damaged tank permeability of 60%. So you can define any permeability that you like, and you can have different permeabilities for intact or damaged tanks.
I don't mind showing that when we speak. Yeah.
Yep. And you can hydrostatics based on observed freeboards. Yes, you can. If you define your AP and FP, then you can define a flotation plane based on your draft FP, drafted AP. You can also create a plane in Rhino. If you had measured freeboards, you can create that plane and use that as the flotation plane. GHS output. No, we don't have GHS output. Real-time support. I think our support is very responsive. I don't know that I'd necessarily call it real time. It's certainly not 24/7. but I think it is very responsive. And we can offer training if you need it. I think that brings up a good point, that on the Orca3D website, in the support menu, there is an item called videos, and there you'll find a number of tutorial videos focused on advanced stability and other topics as well.
Bruce, do you want to pick the screen perhaps? Because I'm holding it, but perhaps you wanted to wrap up. I can perhaps. How do I stop my? Are you able to pick the screen?
Yes.
Yeah.
Yes,
Okay.
I think
Great.
I
Thanks.
just took it. And to get to the screen, the slide I want to, I need to go through this. So a couple of things that that are in the works here: max kg calculations, IMO weather criteria, so you can specify a few parameters here, and then there'll be a new keyword for IMO rollback, and you'll see 2 healing arms, the steady and the gust. That's underway. An enhanced load case grid showing all the load cases. So there was a question also about having incremental changes in load cases, and you do need to do a new load case for each one of those, but with this load case grid that will show them all together, it will be easy to compare them and copy items from one to another. We're working on tonnage calculations and longitudinal strength. And there was also a question about the extents for weight items for weight distribution, and that's part of this function. So on the Orca website, first of all, you can download the software and activate a trial license. That's good for 15 days. And we encourage you to do that and to ask questions as you're experimenting with it. You can always reach us at support@orca3d.com. I see that, Larry sees that, Stéphane sees that, some other naval architects see that as well. So we're always happy to answer your questions. In the support menu, you'll see videos. And again, in particular on this new module, there's a number of tutorial videos that I think you'd find very helpful in the range of 4 to 8 minutes. You can contact Stéphane at ndar@ndar.com. You can contact us at sales@orca3d.com. And again, you're always welcome to use support@orca3d.com. One of the points I wanted to make about licensing, I mentioned the annual and perpetual license options. You don't need to have all of your modules be of the same type. So for example, you can have a perpetual license for design and analysis. For example, if you were upgrading your level 2 license, but for the advanced stability module, maybe you just want to have an annual license. And so this shows the prices for the advanced stability module. So an annual license is $3,500 per year. Also, if you have a network license, if there's multiple users in your office, you don't need to have the same number of seats of each module. So you might have 3 seats of design, 2 seats of analysis, and 1 of advanced stability. So there's a lot of flexibility there.
Okay, cool. Many thanks, Bruce, Larry, Stéphane. Thanks also to all the attendees.
Just Carlos, I see that a couple of questions were not addressed, so perhaps we can offer to take the time to reply a bit later, just to keep the timing of the time frame of this meeting. So the question will not be left unattended to all. Thanks.
Are you answering these questions?
Yeah, go ahead, Carlos. No, I think we are, I don't know. I think we are
I see that there is
yeah.
at least this question by Thomas.
Yeah, exactly.
Yeah. Exactly. That if on the stability criterion coding, you can use if else conditions in the criterions.
Well, Larry, I don't know if we have more time, but Larry, do you want to reply to that or?
Yeah. So we didn't get a lot of time to show this criteria manager, but currently we've exposed, the manager is tied to a Python interpreter. So we've currently managed to expose some of the Python functionality, like min and min. So if you wanted to go to the minimum angle of down flooding or 70 degrees, you could type min 70 down flooding. So we have that kind of capability already. And we're in process on working on more advanced logical capability for all combinations of if and else and so forth. So that's in development, but the existing functionality already includes essentially OR is already included with things like min and max and some other Python interpreter functionality.
Okay, thanks. I think now all the questions are answered. If not, please contact Stéphane, Larry, or Bruce at the emails they provided. And again, thanks everyone. As soon as I upload the video to YouTube, I will email you the link. And have a nice evening. And see you soon. Thank you.
Thank you very much.
Thank you, everyone.
Thank you.